The device on my desk is a Solar IBoost Plus. Now, I'd like to make it clear there are many choices on the market, various strengths and weaknesses, wireless, wired, multiple sensors, all that sort of stuff. This particular one is pretty popular, but I hope that my comments might help people differentiate between some of the models. Now, the idea is that if you have a solar PV array, that you're going to be exporting some electricity. So you could save money if you could intelligently use that electricity to heat your water instead, because it'll cost you more to heat your water, of course. And that's what the iBoost does. It monitors your exported electricity and uses only the excess to heat the water. And it doesn't just turn the immersion on and off, it varies the amount of power going to the immersion proportionate to how much you're exporting. And apparently this version works with battery storage as well. So, makes sense, right? Well, maybe for some people, but I can't see this being the right solution for everyone. Caution is needed, and I wait to be convinced about those battery compatibility claims. So I'm going to install this, and I'm going to use it for a couple of days while I make the video, then I'm going to disconnect it. Why on earth are you going to disconnect it? Because it will increase my energy costs. It's not going to save me money at all. Okay, so why have I bought one then? Well, next year my tariffs are changing and then it will save me some money. So there's a couple of reasons I bought it now instead of waiting. First, I think the prices are going to go up and they've already started to do so. Second, I wanted to get this video out and show people how to think about the cost and benefits involved. If you look at the adverts, you'd think that these are perfect for everyone, but I want to counter some of those adverts, some of the supposedly objective reviews that claim that it's going to save tons and tons of money for everyone. People need to make objective decisions. Those things are only written from one point of view. People buy energy differently. I also want to test the claim that it works with battery systems. It's only got one sensor, so I'm not convinced. So it's a big ask, but this is what I'm going to try and do. And first of all, I'm going to unbox it. I might also open it up and have a look inside. I'm going to install it then just to see how easy or otherwise that is. Hopefully it'll be fairly straightforward. I'm not going to teach about the electrical connections and things like that. If you're not competent to do it, please get an installer. Then I'm going to give it a go. We'll hopefully see it diverting some power. And we also want to see what happens when the sun goes in. Does it disconnect or does it drain the batteries on my battery backup system? Also, what happens when we turn on an appliance like an oven or something like that? And does it allow the batteries to recharge or does it nickel the power? Finally, I want to look at cost and benefits. So various costs, there's the purchase of it, there's the installation costs, there's running costs, which is basically loss of export revenue. And there's, of course, some savings, which is we don't have to buy as much fuel in. That all has to square off against how long the unit will last before we have to replace it. Otherwise, we don't make any savings. So let's open the box. Now, I'm just going to admit here that I am voicing over most of this because the little lapel microphone that I was wearing was pretty awful. Anyway, here's the instructions. Now, my kind of feeling on these is that they are probably sort of adequate-ish, but there's no kind of overview or introductory type thing that really helps you get a grip of things. So that's a little bit limited. There are some programming instructions and I'll have to come to those later. They deal with things like how much energy you have to be exporting before it brings any in. We've got some installation instructions and they deal with mainly the physical installation, but we do have an electrical circuit just here and it shows the positioning of the clamp between the meter and the consumer unit. Obviously, if you've got some other switch gear there, you might need to adapt to that. And yeah. And that's pretty much it. Basically, you're replacing your immersion heater timer with the Solar iBoost, and you're attaching a clamp and a little sender unit to the wire between the meter and the consumer unit. And it's as simple as that. So you should have a two-pole isolator and a fuse already in the line for your immersion heater. If you don't, you really need to have those fitted. And of course, you do need to have an immersion heater. If you haven't got one, if, for example, you've got a gas indirect heating for your hot water tank, then you would need to have an immersion heater fitted to that if it's got the facility. It's almost certainly not worth fitting an immersion heater if you haven't got the right type of tank. And as we talk about cost benefits, I'll talk about the different types of ways that we heat water and things like that, and which ones are worth bothering with and which ones are not. So okay, next up we've got some special instructions for installation in Ireland, so I'm not going to bother reading those. And we've also got a drilling template for the wall, and notable on here is there is a huge amount of clearance needed around it, 100mm on either side. That's probably not quite so critical, but also 100mm below and above, and there are vents underneath and above this. Now 6 inches high, nearly 9 inches wide is the unit size, so that's a pretty big unit. Be sure you can actually get that in your airing cupboard. Okay, let's get the actual item out of the box. Okay, it's actually pretty light, quite plasticky of course, but you know, seems to be fairly well constructed. Just look at that size again. Yeah, and 3.5 inches deep. Okay, I seem to have gone imperial today. And you can see the cable knockouts in the bottom of the box. Okay, let's take a quick look at the connections. Okay, so this is pretty good. We've got cable grips along the bottom and then stacks of room above to put the actual cables in, so there's going to be no problem with that. And 3 lots of connectors up at the top. Okay, from left to right we've got the supply in and 2 outputs for heaters. So live and neutral, earth, plus minus earth, and plus minus earth again. And yeah, they're pretty decent connectors, no problem with those. Now there's a fan here. It's quite a small fan. I'd probably have preferred to have seen something a little larger. I'm hoping that only runs when it's actually doing any heating. Now we can see there's loads of ventilation space all around it. So it needs the ventilation space because it's a proportional control, so there is going to be a fair bit of heat generated. So the last few items in the box relate to the current clamp. So on the right we've got the current clamp, and it's conveniently marked which way round it goes on the cable. And we can see that we can plug it in to this, and it's got like a click lock on it. That's quite nice. Now I understand that the RF sender, which is what I've got in my hand at the moment, can take an external supply, but it's a very funny 3.6 volts or 3.4 volts rather, and but you can do that for the mains. It has a button there for pairing, but I understand it is factory paired, so you don't actually have to do that. You just stick the batteries in, which they supply. And there is apparently a battery warning on the main screen if the batteries run low. It's got a keyhole socket here, so we can just pop a screw in some convenient place and just hook it onto that. It's pretty light, pretty compact, it's fine. And they do provide raw plugs and screws for fastening the main unit to the wall, but funnily enough not for the actual little RF sender. Okay, let's take a quick look inside, and I'm just taking a few photos of the boards here. So there are actually 2 boards inside, piggybacked one on top of the other one. Let's take a look at the top board. So up here they've actually just purchased and installed a little pre-made module, which is obviously the RF receiver. And why wouldn't you do that? If you want your FCC compliance and all that sort of stuff, that's what you're going to do. Obviously an LCD display, and this is just a multi-line character display, blue backlight. That's all there is to that. Some buttons, a microcontroller. I think there's probably a real-time clock on here, which is what this battery backup just here is for. So the microcontroller, I think, is an 18F60, it's a PIC microcontroller, 18F66K. What else is on this board? Obviously the fuse, that's soldered on. The connectors. This guy over here is a whacking great big 35 amp diode. We've obviously got a few capacitors kicking around, and these up here, these are big X class capacitors over here. So it's just nothing really worth mentioning. This is opto isolator, so it'll be doing some of the switching, because on the back of the board around here is the actual controlling switch, which is, yeah, I don't know exactly what mechanism they're using, but we can see the bolt just here which goes through to hold it on the heatsink. There's another bolt here which is holding a huge pre-rectifier onto the heatsink as well. So we're obviously rectifying this and controlling the power going through to the heating element. Simple as that. So presumably it's a MOSFET, or maybe it's a triac or something, but who knows. I'm not going to reverse engineer that in this video. And truthfully, I don't want to take those off because, you know, I kind of want all the heat sinking and everything like that to be working properly when I assemble this. Okay, so let's take a look at the underside of the board. And there's an impressive amount of filtering on here, I suppose, is my main thought. There's not a lot going on here, to be perfectly honest. So we know that underneath this heatsink over here is the bridge rectifier, and it's a big power bridge rectifier and a big power MOSFET or triac or something along those lines. This is essentially a glorified light dimmer. We've got a big heatsink here. Now, when this is in the box, these fins are orientated upwards, which is the correct direction for the air to flow, of course, and on the end of it is where the fan goes to actually blow cool air up through it. Now, it's going to be in an airing cupboard, so it's not going to be that cool, but anyway. So what have we got over here? We've got some nice big X-class capacitors just here. We've got a MOV, we've got common mode choke, common mode choke, common mode choke, and more capacitors down here. So yeah, there's not a lot on the back of this board, but what there is pretty beefy. Just here, this is a relay. So I suspect what's happening there is when we bring the power down to 0, essentially we'd switch that relay off so that there wouldn't be any power going to the immersion heater at all. As we move across to here, then this is a little power supply block, and again they've bought an off-the-shelf power supply block. So this is, let me have a look, 5 volts 2 watts and 12 volts 2 watts, and that's your lot really. So you got mains going into it in one end and 2 DC supplies coming out the other end, just to power all of that digital circuitry on the other side, and the gates and things like that to the switching devices. I suppose the other thing that I'm going to mention up here is what looks like a piece of board that's got its solder mask pulled back. This is actually a piece of copper that is soldered on the back between all of the earth connections, just making sure that everything is nice and sound. Okay, before we see this thing screwed to the wall, let's have a look how it's going to be installed in the system and kind of just think about how it's actually operating. So this is a nice pretty diagram showing sort of how the solar system is installed. We've got the panels, they go across to an inverter which feeds out AC into your fuse box essentially, or your consumer unit. The consumer unit in turn is connected through your electricity meter to the national grid. So if we're producing more energy than we need for our items, then the excess is exported and we meter the amount of energy we're exporting to the grid. All of the energy coming from the inverter should first of all be going to all of the internal devices like the washing machine, the light bulb, and of course your immersion heater would normally be joined on using some sort of time clock. So it will turn on, hopefully you are buying cheap electricity at night, and that's when you are heating your water. So the only time when we get any energy flowing out of the house onto the grid is when our solar panels are producing more than the amount of electricity we consume. Let's move on to the next slide. So here we have our time clock has been replaced with this Solar IBoost. It's kind of pretty much the only change to this. What we've got is the sensor attached between the consumer unit and the electricity meter. So all that's going to do is it's going to sense which way the electricity is flowing. If it's flowing out of your consumer unit and onto the grid, then there is excess electricity available, and irrespective of what time it is, it will therefore turn on the iBoost and connect some power through into the heater. Now this does imply something quite interesting, because if we look at this diagram, there's no differentiation between the heater and, let's say, the washing machine. They're all the same, they're just appliances, and it's all just consumption. So if we sense there's excess power and we divert it and switch on our immersion heater and there's no longer any excess power, then there has to be a bit of intelligence, a bit of an algorithm built into this unit that will work out that it shouldn't just turn itself off immediately because there's no power left. So it has to be doing a bit of maths in there to work out that the fact that there's zero energy on the output means that it's using the right amount. If a little bit more goes out to the grid, then it can increase the amount that it's allowed to use. If a little bit less goes out to the grid, we start bringing power in from the grid, then it needs to reduce the amount it uses to bring it back down, essentially to close to zero, hopefully a little bit more than zero. So that's fairly simple. All it's trying to do is keep the exported energy at about zero. So it senses how much is being imported or exported and just tries to zero it. That's simple, really. Now, of course, there'll also be a thermostat on the immersion heaters. So despite the fact that you might be trying to throw energy into the immersion heater, it doesn't necessarily mean it's going to be consuming it. If it's up to temperature, job done. Let's look at a slightly more complex scenario then. This is basically the same diagram again, except we've got batteries as a second source of power going into the inverter. Now this is why I'm kind of a little bit nervous. And the reason is the Solar IBoost has no knowledge of where the inverter is getting its power from. The inverter will choose for itself completely autonomously whether it's bringing in power from the solar cells, the batteries, or a combination of both. It's just going to try and supply the energy required for all of the inside consumption, and that includes the immersion heater. It is going to try and provide all of that from those two sources. So in parallel with that, you've got this kind of iBoost trying to control the hot water. So the fear here is twofold. One is that when we're charging these batteries, the solar power's ramping up, we start charging the batteries, but we don't start immediately. We wait till there's a few hundred watts on the output being exported before we do it, and that's because we don't want to charge the batteries with 20 watts. You know, we want quite a bit of power going into those batteries when we charge them. So that's the first thing. We actually have to hold off the iBoost so that it doesn't steal the power before the batteries get to use it. The second point is this. We're busy running on a nice sunny day. The power's coming through the inverter and it's been stolen by the iBoost and it's powering the hot water. And then a cloud comes across. So the inverter looks and says, oh, I've got 3 kilowatts of power I need to deliver. And my solar panels have just gone down to 1 kilowatt. So I need to supply 2 kilowatts out of my batteries. So it will switch in those batteries completely transparently, very quickly, and keep providing that. Now, we still don't have any export. We've still got the same amount of power we had before, the same balance of power across the whole system that we had before, except instead of coming out the solar panels, it's coming out the batteries. So the question is, how does the Solar iBoost know that? Now, my suspicion is what they've done is they've programmed it so that it will tend to reduce, it will be biased to reduce the amount of power that it is consuming. And then if it looks on the export and sees that there's excess power, it can put it back up again. So it will want to reduce the amount of power. But that could mean that it could be quite a long time before it responds to, for example, a cloud coming across, and you could end up stealing the power out of your battery. Now, you could argue, well, does it really matter? Because if the sun comes out again, it's going to recharge the battery. Well, it might recharge the battery, or it might not, depending how much sun there is and how much time we've got and all of that sort of stuff. But we can only look and see what happens. Anyway, that's how it all hangs together. Okay, so we are installed in the airing cupboard. That went very well indeed. So the right hand cable is just coming off to the immersion element. The left hand cable at the bottom is going off to the dual pole isolator switch and fuse. That was already there from the previous installation. I had to mount it on the back wall because there wasn't really a lot of room for a unit measuring 9 inches by 6 inches, and that's something to think about. This is a sizable unit. The other thing, I don't know if you can hear it, is that while it's running and heating the immersion heater, it does actually have a fan noise. I don't think it's a disaster, but Yeah, if it's in a bedroom, you might want to think about that a little bit. In terms of fitting it to the wall, it's four screws. The top two go in to all just go into the wall, and they go in about so there's about 4 or 5 millimeters sticking out of the wall, and then the unit just clips onto them, and then you apply the two bottom screws to hold it in place. There's a drilling template which was absolutely fine. It includes all the clearances and everything, and you do need quite a lot of clearance for it. Sort of 100 millimeters all the way around, 4 inches space all the way around. So you can see at the moment it's heating by solar. Now, pairing this up with its sensor was no problem. It was factory paired. All I had to do is put the batteries in, and attach the sensor to the cable downstairs. Which, given that I was kind of fumbling with the camera, hopefully that worked out okay, and there's enough to show you what was going on there. Yeah, so it just paired up automatically, not a problem at all. It does have a backlight when you press that display button on the left hand side, and you can boost it using the button on the right hand side and give it like 15 minutes boost of water or whatever. And I have tested those functions out. In terms of installation, it took about 45 minutes, and that included doing things like the earth tests to make sure everything was okay. What I'm going to do now is I'm going to go down stairs, and I'm going to turn on an oven or a grill or something like that. Maybe just the kettle, because I fancy a cup of tea. And hopefully we should see the amount of energy being put into the heating reduce quite a lot. Now we've already seen it drop a little bit, and that'll be because it's quite a cloudy day, clouds coming and going, and so we should see that varying quite a lot. So there we go, I have turned on the oven, and we should no longer be heating the hot water, I hope. And that isn't good news, is it really? Oh, there we go. That took its time. And you may have heard the fan cutting out there, so that was quite noticeable, that fan, in fact. I'm still about 2 meters away, and I'm definitely noticing it. So there we go, water heating off. You know, very slow response, not over impressed by that. Okay, so that's the oven turned off. So I've turned the oven off, and the water heating is still off. I'm pretty sure I must be producing, I mean, it looks bright enough outside, I must be producing excess energy somewhere. Here we go. Well, that was quite a delay. Okay, so we've shown that appears to work. We're using 1.7 odd kilowatts. So I'm going to go and look at the inverter now, and I'm going to disconnect the panels from that. Now this is the bit that's worrying me, because when I disconnect the panels, the batteries essentially will step in, and I'm really worried that the batteries will actually end up powering this 1 point whatever kilowatts. Let's find out. Okay, so the panels are disconnected now. So hopefully this will detect that to be the case. I got a little flash to say that it received something. And right now I am still powering my heating from my batteries. So I've got no solar power coming into the house at all at this point. Still waiting. Okay, so we're down to about 300 odd watts now. So what I'm going to do is a bit of programming, and I'm going to change the storage offset and see if that does actually improve things. So I'm going to program most of these. Okay, finally. So it took a fair old while to turn the water heating off. So I'm going to go and reconnect the solar array. We'll let my system settle down for a few minutes, and then we'll retry that experiment. Okay, solar array is back on. It'll take me possibly a few minutes just for everything to settle down. Okay, so at the moment I'm looking at the inverter, and we've got 3.77 kilowatts coming in, 170, 200 watts going out to the grid, and we're consuming just over 2 kilowatts in the house. I'm feeling slightly exhausted from going up and down these stairs every 5 minutes. So there we go, yeah, 1.25 kilowatts, so that's fine. Let's turn the solar panels off again then. Okay, that solar panel's disconnected. Let's see how fast it responds this time. So it's still pretty slow, but it's a hell of a lot faster than it was last time. Remember, at this point the solar panels are producing nothing. So this 170 watts or whatever, well, they're all coming out of the batteries. Now that's a lot better. So what it's obviously doing is looking at that exported power, seeing there isn't very much of it, reducing its consumption a little bit, and it's looking, expecting there to be some power there that it can use, and there still isn't, so it has to reduce it more and more and more, but its polling frequency is quite slow, so it's taking a while to degrade. Now the threshold is there actually because when we're charging the batteries in the morning, for example, the sun comes up, we start making power. First of all, we meet the needs of the home, and then we start having a little bit too much power, and it starts exporting to the grid. And on my system, about the first 150 watts or so will export to the grid before the inverter decides it's time to switch that across and start charging the batteries. What that figure is will depend upon your batteries and all sorts of stuff, but yeah, the grid output will go up a little bit. And what you don't want, of course, is your immersion heater to turn on and start stealing that power before your battery charge can come into effect. I'm not really very keen on the fact that it spent several minutes dragging power, quite a lot of power, out of my batteries because the sun had gone in basically. Not very responsive, I think, to that. A more expensive model with multiple current clamps, of course, may well have detected exactly what was going on and done it more intelligently. Anyway, let me go and turn my solar panels on again. Okay, my batteries are down to about 94%, so I would expect them to take 500 or 600 watts of charge. We'll just see what's happening. So they are actually charging now. Just letting everything settle down. Yeah, so the batteries are charging now, and we can see that the heater is actually taking some energy, but the majority of it is actually going into the batteries. So pretty happy with that. The threshold and everything like that is working, and the battery's getting there first. Okay, the last section of the video is all about the thorny question, is it worth it? Is it even worth buying one of these things and putting it in? And the most important thing to think about is before you save any money, you've got to get your investment back. So if it costs you £350 to put this thing in, then before you save a single penny, you've got to have got all that £350 back again. And you've got to have got it back before it gives up the ghost and breaks and stops working. So this is something called cost benefits, and I'm not going to go into too much detail on this because we would have to do all sorts of calculations, and there are additional complications, like you could take that £350 and use it for something else that might save you more money. Sure, make an estimate of how much you're going to save, but then think, what could I use this money for that would just save me more money than this? Because you would think, looking at the adverts, that this is, you know, God's gift to everyone. The savings on this are pretty marginal, unless you happen to have stacks and stacks of free electricity, and you don't get any money you don't lose anything by not exporting it anymore, and yeah, all that sort of stuff, and you're already insulated. For most of us, yeah, the savings aren't really going to be that big. Let's look at the cost benefits stuff that we have to work out then. So looking at this slide, there's two obvious things. We've got a saving, which is the bottom line, and we've got running costs, which is how much it costs us each month to run. So let's say monthly. So each month we will make some savings because we don't buy as much of the fuel that we're buying at the moment. We will make some losses if we normally receive some money for our exported electricity. So if you're getting paid 5p per kilowatt for your exported electricity and you don't export it anymore, you won't get any money. So you're replacing one charge with another. Now, there is a little complication there, because actually if you are buying gas at the moment, then when you heat your fuel, that's not as efficient as electricity. So there is an efficiency thing to take account of as well. But generally speaking, you're just replacing one source of fuel with another source of fuel, heating the same water that you were heating before. The chances are that you're paying more for the fuel that you buy than the fuel that you export. So you're going to be quids in, right? Well, not really, because you also have to subtract off the amount that it costs you to buy the damn thing in the first place and put it in. So you've got the cost to buy it and to fit it, and any other bits you needed. If you had to fit an immersion heater, for example, there's all of that to pay, and it doesn't last forever. You know, it will fail eventually. Your immersion heater will give in after 10-15 years. Your actual diverter, whether that's an iBoost or someone else's, that's going to fail after a while. It's going to need to be repaired or replaced, probably replaced. If you had it fitted, you're going to have to pay fitting fees again. They won't refit it for nothing. So we can think about that almost like an annual cost. If we say it's going to cost £350 and it's going to last 10 years, you could say that's like £35 a year cost. Now, in a proper model, you would actually put more of that up at the front. You'd say the first year it costs £60, the next year it costs £50, the year after that it's what, and so on. We're not going to go to that degree of complexity, and that's all to do with the fact that money changes value over time. But the key point here is you don't make any savings until you've paid back your original investment. Essentially, you're paying for electricity up front before you're using it. Think of it that way. I do have a spreadsheet which I'm going to show you, which is for those people who are more interested in trying to do this fairly accurately, and who can get things like, if you've got a smart meter with half-hourly data and things like that, or one of those in-home displays, you might be able to get some pretty good data. But bear in mind that electricity, gas prices do change, oil prices change. You know, you can only do your best. Even if you think you've got it right, in a few months' time, it could be different again. I would suggest that, you know, you want a clear saving. If it looks a bit marginal, probably not the right moment to be doing this. Wait until it clarifies in one direction or another. Okay, so let's have a look at a rough and ready calculation for those people who don't really have a lot of access to data. So I'm assuming that you know how much per kilowatt you pay for your fuel. Now, if you pay per litre, or you pay per gallon, or you pay per cubic metre or something like that, if that's what your costs are in, then there are calculators online that will convert your gas, oil, whatever, into kilowatts. So you need your costs in kilowatt hours. Okay, so the first thing is then we'll just estimate how much it costs to heat a tank of water using electricity per year. So I'm saying it's about 3,000 kilowatts for 1 or 2 people. For 3 people, it's likely to be about 1,000 more. For 4, about 5,000, and so on. That's the first job. Just make an estimate of that. Now, if you know it, then that's absolutely great. If you can get it from your gas bills or electricity bills, or you've got a meter on it or something like that, then you're going to know the answer. Now, you are not necessarily going to be able to divert all of the electricity you need to heat that. So we're going to use a different figure. We're either going to take that figure, or we're going to take 50% of what you expect. So here, for example, I've got 4,000 kilowatts. It's a 3-person home. I've chosen 4,000 kilowatts from step 1. But in fact, when I look at my export figures, I only export 2,000 kilowatts. I export only 2,000 kilowatts a year. So I take half of that, which is 1,000 kilowatts. So I'm saying of my 2,000 kilowatts, in truth, I'm really going to get half of that and divert it across to the heater. Why only half? Well, there's a variety of reasons. One of which is that on a very sunny day where you get loads and loads of kilowatts, you'll have heated up the tank and then actually you won't be diverting anymore. So all the rest of that electricity you're generating is going onto the grid still. Another is that there's always a threshold at the start. So when you've got an export of 20 watts, the diverter won't pick that 20 watts up and use it. And you do actually have a running cost for your diverter as well, which we're kind of ignoring here because it's pretty small. You know, you're not going to use all of your exported energy. It might not be half, it might be 3/4, who knows. But, you know, you've got to take, this is rule of thumb, it's rough and ready. So we're either going to take the 4,000, or if I don't export stacks and stacks of electricity, there's no chance of me diverting that 4,000. So I'll take a lower figure, half of what I do export, which in this case is 1,000. Okay. Step 3 is to calculate how much per kilowatt I actually save. So this is dead easy. The price paid per kilowatt of fuel that I use, so that's what I get billed. It's on my bill. It will be written down. It'll be on my contract. Less the price paid per kilowatt lost. So if I buy, let's say, electricity at 10p and I export electricity at 5p, that gives me 10 minus 5, not 15 minus 5. Whoops. That gives me 10 minus 5, which is 5p. So per kilowatt that I actually divert into this tank, I'm saving 5p for every kilowatt that I. So obviously what I do now is I take the amount that I've diverted, which is the amount I calculated in step 2, and I multiply it by that saving figure I've just calculated. So here we go, 1,000 times 0.05. That's £50 per year. Whoa, that's not very much, is it? If the amount I export is lower, let's say 4p, then the amount that I save will go up to £60 per year. If the cost that I buy at goes up, then I will also make more saving. The difference between these two prices is what actually drives my saving. So the closer they are, the worse my saving. Now, £50 a year is not very much to be saving. You might say, okay, yeah, but over 10 years, that's £500. That's definitely worth having. But don't forget, you've got to subtract your original capital investment. So I'm suggesting here you subtract 10% of it. So I paid £350 for my system. So I take my £50 saving, I subtract off 10% of it, that's £35. And now £15 is all that's left. So I'm making a saving of £15 per year, or a total saving of £150 over 10 years. And here's the crux of the question. Can you save more than £150 over 10 years if you use your £350 for something else? So if you use to put cavity wall insulation in, the answer is almost certainly yes. But you'll have to kind of weigh up where you're going to get your best savings from. This might save you money, but there still might be good places to spend it. So now I'm going to switch across and I'm going to look at a spreadsheet, and on this spreadsheet I'm actually going to show you my figures. These are my true. So I will put this spreadsheet onto GitHub and put a link in so you can download it. I'm really doing the same calculation, I'm just doing it with different data, more precise data. So I've got the diverter device that I'm buying, which is the iBoost, and it costs £350 thereabouts, and I'm saying it's got a 10-year life expectancy because I don't know otherwise, and and truthfully in 10 years so much will have changed that will do for starters. So I can look at it two ways. I can look at it £350 of fuel purchased up front, or I can look at it as £35 a year running cost for 10 years. So, either way. So now, having dealt with the fact that I've got a cost, I now need to deal with how much do I spend heating my water per year, because that's actually the maximum amount that I can save. I can't save more than I spend. So on the spreadsheet, I've put a few useful things in: per day, week, month, year, as the figures that I'm going to fill in on this spreadsheet, because different people have different data available. So I'm going to go as monthly data, and you can see here that it's chosen a multiplier of 12. So it's going to multiply what I provide in here by 12 to get the yearly figure. Now here we've got a question about gas. For gas, are you using meters cubed or kilowatt hours for the data that I'm filling in? And I'm using meters cubed because that's the data that comes on my gas bill. And so here we go. So I looked at my gas bill for August last year, and we get a bill which contains data like this. This is half hourly consumption data, and I can actually download it from the supplier's website. So this is my consumption figures. Now I happen just here between 6:30 and 8 o'clock every day is when we run our hot water cycle, and we don't have anything else turned on at the same time. So that's nice and simple. The heating actually comes on at 8 o'clock. And of course, this is in the middle of summer, August, so we haven't got the heating on at all. So it's nice and easy. There might be some charges later in the day relating to using a gas cooker. Yeah, there they are, for example. But generally speaking, I can look at my half hourly figures. I can take those three figures just here. So this is 6:30 to 8 o'clock on the 10th of May, 2022. And I use 0.927 meters cubed to heat my water. And there's another one down here, and there's another one down here. So I did that for all of August of last year, and the total was 15.12 meters cubed. That cubic meters has to be turned into kilowatt hours, and roughly speaking there are 33 kilowatt hours per cubic meter of gas. But if the figure changes, and you can kind of look it up on the internet, then, or you want it more precise, then you put that in there, but 33 is good enough. That turns into nearly 500 kilowatt hours per month. Okay, but then there's an efficiency percentage here. So what the hell's this about? Well, the thing is, I'm going to be replacing some of this with electricity, and electricity is going to heat the water more efficiently than gas. So if I take my 498 kilowatts and I use electricity instead, I won't need 498 kilowatts. I'll only need about 300 or something like that. So this efficiency figure here is basically saying how efficient is my gas. So it's never going to be 100%. Now my boiler is about 90 something percent efficient, so that's pretty good. But it has to heat the water in the pipes. The water in the pipes has to go to the tank. Then the heat has to transfer from the water in the pipes into the water in the tank. It won't all do that. Some of it comes back round through the boiler, which has to top its heat up, and on its round trip it's losing heat, and so on and so forth. So yeah, we don't get anything close to 100%. Now I was actually able to measure that because we have half hourly billing. We can just run all of our hot water off and then heat the tank up. And then we can look at our data from our supplier to see how much it took in order to do that. And I can also do the same with electricity, because I've got the immersion heater in there at the moment. I can either heat it with gas or electricity from cold and take those two different readings. And I can basically stuff them in the bottom here. No, just here. I've done a little tool. So you can put in the two different figures. It takes 28 kilowatts of gas or 15.6. And that gives me 56. That's the relative efficiency between electricity and gas, 56%. So you can do that type of measurement yourself if you're able to do it. If not, I would suggest you just put 60% in there as an estimate. Now, unit cost of gas per kilowatt hour, that's your tariff. So that should be fairly straightforward. It might be expressed per meter cube, and you will find converters on the internet. And from that, it will calculate the yearly cost of gas. So there we go. So currently I spend £187.41 heating my water using gas. So I can save a maximum of £187.41 because that's how much I spend. Now under that, I've done similar blocks for electricity and oil. Oil, of course, is asking things like number of litres and things like that, and then it's converting that into kilowatt hours. And we've got a useful little tool on the right hand side here, just in case you buy in gallons. We've got US gallons and imperial gallons, which are not the same thing. And similarly for the gas, you might be charging feet cubed rather than meters cubed. So yeah, okay, little converter there to just help things along. But essentially, all we're going to do is we're going to calculate. And if you do mixed gas and electricity, then, just fill two sections in, because we're going to calculate the amount of gas we spend, the amount of electricity we spend, and the amount of oil we spend, add them all together, and that gives us our total for the year. Then down here, we're doing a very similar thing that we saw in the rough and ready calculation, which is we've calculated how much in electricity. There are two of us living here, and to heat our water, then we're actually using 3.353 kilowatts per year in equivalent electricity. We're actually using 5,000 something. We're using 12 times 498, 12 times 500. So that's nearly 6,000 kilowatts of gas. But if we were to do that with electricity, that would only be 3,353 kilowatts of electricity we would need for the same job. And we do the same with electricity and oil, depending what fuel we happen to be using at the moment. And of course, we're converting everything into electricity. So there we go, 3,353 kilowatts. So as you can see, that is very similar to the rule of thumb where I said use about 3,000 for a family of two. Okay, the next question though is, how much will I lose per kilowatt that I no longer export? Well, the answer is that I'm going to lose 0.04 per kilowatt, and that gives me a theoretical running cost of £137. So let's have a look. Let's look at this section here, payback and value check then. which as you can see for me at the moment is not looking too rosy. I'm losing money apparently. Here's the thing, we've already said the maximum that you can save is £187.41 in my case, because that's how much I pay. And we also know that the maximum running cost that I might incur is £137. So there looks to be some saving there. I'm paying 187 and it might cost me 137, so you could say that's £50 then, yeah? In fact, I only export 1,000 kilowatts of electricity per year, and so therefore that's the maximum amount that could possibly be diverted to heat up the water. I want 3,353 kilowatts, but I've actually only got 1,000 to spare anyway, so I'm not going to get all of that 3,353 kilowatts, am I? That's just not going to happen. And in actual fact, of that 1,000 kilowatts I export, I'm not going to manage to divert all of that either. So I've made a rough estimate at 70% for myself. If you've got more electricity, let's say 2,000, then you might be thinking of a different figure for your percentage that you can use. But I think, 50 to 70% is probably sort of all right to work with. So you can see here it's saying what percentage of your costs and savings are you actually going to realise. So it's recognising that you can't get it all. So it's basically it's taking 70% of 2,000. And that is 1,400, and it's comparing that against the amount that you want, and it's saying, well, you want 3,353, but you've only got 1,400, so I'm going to do my calculation of 1,400 then. Now, if this went up to, let's say, 5,000, then it's saying, okay, you've got 5,000 to spare, 7% of that is more than 3,353, so that's fine. You are going to fulfill your desire to divert 3,353. Now, truthfully, you're probably not going to because you've got the winter and things like that. But, hey, there we go. If you've got that much to spare, then chances are you're not going to be a million miles off giving it all across, giving everything you need to do your hot water. Let me put back to my true figure. Okay, so I'm only realising 20%, 21% of the savings that I would like. Okay, so let's have a look at that. So I'm saving £39 a year, not very much. It's costing me £28.70 to do that, which is giving me £10.43 saving per year. But if we remember right up at the top, I said that if I think about this as a yearly cost, it's £35 a year just for the initial investment. I've already sunk £350 into this, and I'm only making £10.43 a year. So despite the fact that's a positive amount, it is saying it is going to take me 33.6 years to get my investment back. And in 33.6 years, £350 is going to be worthless, to be perfectly honest. And the total gain that I'm going to make is I'm going to make a loss of £245 over a 10-year period. Because I've said my life expectancy of the system is 10 years. And it's saying, well, after 10 years, you'll have lost £245 because you're only making your money back at £10.43 per year. It's going to take you 33 years to get your money back. And the chances of this thing still working in 33 years, are pretty much none, I think. Now, so why have I bought this then if I'm going to make a loss? Well, because if we go up here, we've got my gas price at the moment. Now, I know that when my current contract ends, that my gas price is changing to this, 0.074, so 7.4 pence, so it's doubling essentially. Now, and I do expect it to go higher. Now, if we look down further, I'm still got the same efficiency. Look, 1,000. I still only produce 1,000. It's only 21%. But my gas pull is now so much higher. Instead of 100 and something pounds, it is 443. My running costs are exactly the same because they're not upping my export amount. They upped it a few months ago to the 4.1p that I'm showing here. But now I make £63.80 per year. And that is, in 10 years' time, that will be a profit of £288 extra saving. Now, it's not a huge amount. It's £63.80 off my bill every year, so only £6 a month or so. But payback in years, 5.5 years, the system will have paid for itself. And over that 10 years, £288 profit. So I'm kind of all right with that. It's not stunning. Everyone knows at the moment really that gas prices in particular, which is what I use, are not really scheduled to come down. In fact, they're scheduled to go up even more. So let's say that it's going to go up to 11 pence. And we can see that the payback period is dropping significantly, and the total amount that I'm saving during the life expectancy of this has gone up a lot. So £738 over that 10 years. And that's obviously worth having. If you are on the feed-in tariff, then let's just go to this cost thing here. Cost you will lose per kilowatt hour will actually be 0. So You do get paid, of course, per kilowatt hour that you generate, but you don't get paid when you export it. So you don't lose anything per kilowatt that you export. And we can see how easily the figures work out then, £1,000 profit. And even if I go back to my current price, which is 0.0313, you can still see that even though I don't actually pay that much to heat water in my house, that I can still save £39 a year, and it still only takes 8.9 years to pay back. So earlier in the video I said, if you're on the feed-in tariff, it's almost certainly worth it. Well, it almost certainly is, but I'd still say it's worth thinking whether or not using your money for something else would give you more benefit than that. The figures aren't that exciting, are they? Let's be honest. So in conclusion, I think these devices aren't right for everyone. First of all, you've got to have the capital to afford to install one, of course. And if you've got that capital, you might be better off making savings on some other energy saving endeavour. Insulation, doors, efficient heating, instant heating of water, that sort of stuff. Heating water in a tank and storing it there isn't necessarily the best. This is just an upgrade, not a perfect solution. Currently, for some people, there is a possibility of some small losses. If you're on a fixed tariff, for example, for a couple of years and it's quite low, and your export price and your purchase price are very similar, there's a goodish chance you could actually make a little bit of a loss on this. Not a lot, but a little bit. Having said that, prices are rising, so yeah, that's likely to be more worthwhile. Of the unit itself, the prices of that are rising as well. Stock is limited, plenty of places are out of stock now, and also for things like the buddy system that can go with it to give you a sort of in-house display. I purchased now instead of waiting because of that. I didn't want the prices to go up even more. In terms of packaging, delivery, etc., delivery was fine, packaging was fine. The instructions are adequate, but they need some sort of introductory section to talk about what you're actually going to read. You just leap into screenshots and things, and not great, adequate. Installation, yeah, easy, quick. The sensor's ready paired, so that's a big bonus. It's wireless, that makes it easy to install. On the other hand, the unit itself is large. It needs stacks of space. The total size of the space it needs on your wall is the size of an A3 piece of paper. There's also a fan, which is a bit annoying. Shut it in a cupboard and it's acceptable, but yeah, do you want it on in a room like a bedroom or something like that? Yeah, I'm not so sure. A larger fan with slower airspeed would have perhaps been a little bit better. I wanted to do some tests. I wanted to see it divert power proportionately, which it has done so. It did so no problem at all. Yesterday, it was a pretty cloudy day, not a great day, and it stole 5.4 kilowatts of energy that would have been exported. I didn't see any weird import figures or anything like that on the figures, so happy with that. I wanted to test if it allowed batteries to charge. I had to raise the detection offset, but they do indeed charge, so that's no problem in my battery powered system. What worried me more was whether or not it would steal power from batteries when the panels became shaded from clouds and things like that. So, it's grabbing 2 kilowatts of power and the panels get shaded by some sunshine. Does it reduce its power usage, or does it steal the missing power from the batteries? Now, I've got to be honest, the answer is it steals the missing power from the batteries. It does drop down, but it took about 5 minutes to do so. Now, when I add it up, it adds up to about 100 watt hours that it pinched from the batteries, but that isn't actually great. It's not very good at all, really. I'd rather it didn't do that, and probably the batteries would recover from that in the day when the sun came out again and things like that. But yeah, now I suspect it's to do with the fact that it's a wireless sensor, and it only seems to sample about every 20 seconds or so, so it's very unresponsive to changes. It does have weekday programming. It has boost programming for summer and for winter, and you could therefore also use this to do some timed low-cost overnight electricity usage as well. If you've got like a dual tariff or can get a split tariff, then you might be able to use this to turn on your hot water overnight as well at a very low price. So overall, it's a useful device. It's only beneficial when the price difference between you buying fuel and exporting is very wide. If those prices narrow in the future, then there is some risk of not getting your investment back. So anyway, this was all pretty wide ranging, and certainly the stuff on cost benefits was a bit long, so I'm sorry for that, but I think that's perhaps the most important piece for some people. But I hope it helps people think about what's right for them. Think about the true benefits instead of what the adverts are claiming. It doesn't look like it's going to save thousands for most people, and you'd think it was, according to the adverts. So anyway, if you enjoyed this video, please remember, click like, subscribe if you haven't already done so, and of course please leave some comments. I'm sure there'll be some comments about this. I will put some links in the description, and if you have some of your own, please put those in the comments as well. In the meantime, have fun, and I'll see you soon.